When I first learned about inverse matrices, my mental picture was of a parallelogram widening and compressing back into a square, and something similar for a parallelepiped. So when I was shown the method for finding the inverse of 3 by 3, everything seemed completely arbitrary and not at all to do with compressing a shape back into a cube. I couldn't find a proper geometric proof for it online, so here's my unrigorous proof. Hopefully it's enough to satisfy your curiosity. So here's the situation. We've got a matrix M, which transforms a vector x into a new vector x prime. We want to find the matrix M inverse such that M inverse transforms x prime back into x. It'd be nice if we could express the components of x one by one as some expression involving each element in the original matrix M and the components of the vector x prime. That way we could plug it into the bottom expression and maybe find some cancellations or some interesting comparisons between the left and right hand sides. So this is going to be the approach that we're going to be taking today. Cramer's rule is our way to do just this. Let's take a look at a 2D system. If we wanted to find x and y for this system, we'd probably use methods like elimination or substitution, which involve rearranging the expressions and, in some way, inserting the information from one line into another. As the number of dimensions increases, we'd probably start to try and express the coefficients on the left-hand side as a matrix, find the inverse, and just read out the values. But let's just pretend we don't know how to find the inverse right now and find a new trick. First, here's the matrix form. We see that we can interpret this problem as trying to find the vector which transforms under ABCD into the new vector whose values we know. If we look at the details of what the matrix is doing, we see that it's turning the 1, 0 basis vector into an AC, and likewise the 0, 1 into a BD. So the end result is that the instructions x number of basis vector 1 and y number of basis vector 2 no longer make the vector xy, but instead x prime and y prime. So we've already shifted our focus from individual variables to vectors. Let's shift it again to the shapes that these vectors create. In the case of normal unit vectors, they create a unit square. We can find their area easily enough without finding the determinant of a matrix, but we can be reassured that the determinant agrees with the geometry of the situation. So what shape are we going to get if the vectors were xy and 1, 0, or 0, 1 and xy instead? Well, if we replace 1, 0, or I hat, we'd make a parallelogram whose area would be x, the base is 1 and the height is x, and the determinant also confirms it. Likewise, if we replaced the j hat vector with xy, then we'd make a parallelogram with area y by performing the same analysis. If we were to transform the coordinate system by this matrix, then we'd know precisely where the xy vector would go and could just read off the matrix for the 1, 0 and 0, 1 vectors. So in this example, the xy vector would transform to x dash y dash, and 0, 1 would become BD. Applying this transformation scales the area, which was x before, by the determinant of the transformation. Since the new shape has an area of determinant of x dash b y dash d, this means that we can express x as just the ratio of these two determinants, the determinant of the changed matrix over the determinant of the original matrix. So it's the exact same process for y. The parallelogram with an area y is scaled by the determinant of a changed form of the transformation matrix, which we can use to give us an expression for y. We can generalize this to any number of dimensions. The original shape will go from parallelogram to parallelepiped to a 4 or 5D equivalent, and areas become volumes and more, and the changed matrix will include all the extra variables instead. So what was the point of this? Why do we care if we can get such expressions? Well, if we go back to the start of the video to the condition we wanted our inverse matrix to satisfy, then we can start to substitute the expressions back into our system. Here's the full set of Cramer formulas for the 3 by 3 case. If we start with the first row, column, and end result, by applying the matrix multiplication, we see that A, B, A dash, B dash, and C dash are coefficients of x dash, y dash, and z dash respectively, and their sum is equal to x. We can substitute our Cramer formula and start to write this out explicitly. If we focus on the determinant for a second, we'll get this expression. And if we expand out the b and c minors and shuffle them around into coefficients of y dash and z dash, we can write the whole expression like this. You might notice that if we knew that the determinant of the transpose of a matrix is the same as the determinant of the original, then we could skip this kind of intermediate shuffling step, but I wanted to limit the number of external identities we needed for the proof. So next, we can notice the dashed variables have coefficients which appear to be minors of the transformation matrix. If we compare the coefficients to A, B, and C, we see that they are each 1 over the determinant of m multiplied by some minor. We can figure out which ones by looking at the original matrix. It looks like each variable involves the minor of the variable on the opposite side of the Lie diagonal, which suggests that a transpose needs to take place at some point. So if we were to take a look at the next row, we'd have the exact same process with the opposite polarity of each of the terms compared to last time, coming from the alternating signs that come from a determinant, caused by the dashed components being on the column that we negate this time. If we compare coefficients again, we'll see the same minus pattern. And if you do the last row, you'd see the exact same thing with the sign pattern of the first row. So I'm just going to show the end result. From this, we can kind of work out the steps that we need to take just by looking at it. So step 1, we're going to need a matrix of minors. Once we've done that, we need to introduce the sign pattern. And at this stage, we'll have made the cofactor matrix. Once we've transposed it, we'll have the adjoint matrix, and finally the inverse matrix once we divide by the determinant of the original. So the plus minus pattern comes from, and the minors both come from the determinant, and the 1 over determinant of m term comes from the Cramer formulas. So here's the result. The inverse of a matrix is the transpose of its cofactor off by a scale of 1 over its determinant. I know it's not the most rigorous explanation, but hopefully it's satisfactory. Thank you very much for listening.